This video is a continuation of problem 1 of the series, Force Method versus Method of Stroops. In this video, we will look at the case of buckling of the two diagonals of the structure we looked at in that video. Buckling in indeterminate structures may not be catastrophic. We will show how to analyze a structure with buckled members. This is the first video where I calculate deflections or the displacements at the joints. It is not necessary to use virtual work methods to calculate deflections. That may come as a surprise to some people, but you can do most of structural analysis without virtual work methods or what they call force methods. Only the spreadsheet will be used. So you do not have to run to software to calculate deflections. It can be done using just a spreadsheet. My name is Charles DeMatos, a retired lecturer from the University of the West Indies, St. Augustine campus, Trinidad. In problem 1 of the series, we looked at this problem, a truss with 4 joints A, B, C, D, 6 members, 4 by 4, 5 kilonewton, vertical load at B, and the supports are shown. This was taken from this video entitled in the quotes here, and it's solved in this video using the force method. In the earlier video, we analyzed the truss using the method of Stroops. These were the superposed forces that we obtained. For the member BD, you had a force of -5. This comes from the transfer of the vertical load at B through to D. And then on all of the other members, you have the Stroop forces. Including this member BD, you have Stroop forces. Notice on the diagonal, it's -f square root of 2 on each one. And the others are F, 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 and F, as you expect with a rectangular Stroop. In the earlier video, we looked at this scenario where the diagonals are slender with a buckling load of 0.5 kilonewtons. So at this stage, at the buckling stage, the force on the diagonal root 2F would be 0.5. And these would be the once you have these forces on the diagonals of 0.5, you can calculate the forces in the other members. This would be the forces which provide equilibrium at each joint. In all of the scenarios looked at in the first video, the diagonal forces exceeded 0.5 kilonewtons. So if you had members of those sizes and you loaded at B with the given load, when the diagonals reach 0.5 kilonewtons in compression, they would buckle. And you would end up with these forces in the other members. So buckling would occur in the two diagonals here, and we will do a design that allows buckling to occur at this 0.5 kilonewton value, but we do not want buckling to occur in the member BD. So I'm going to give you some actual member sizes for which this situation will occur. These are the cross-sectional areas. AB and CD both have cross-sectional areas A1. AC and BD have cross-sectional areas A2. And the diagonals have cross-sectional areas A3. I'm using rectangular steel sections for the members. So the modulus of elasticity is 210,000 newtons per square millimeter. Let's start with the vertical members, and these have cross-sectional areas A2. I'm assuming square sections here for the vertical members. The force in the vertical member, the compressive force in the vertical member BD is 46 newtons. The length is 4,000 millimeter. So for buckling, here I'm using the Euler buckling formula. So for buckling to occur, it would have a second moment of area of 35,868 as millimeter to the fourth. You can convert it to centimeter to the fourth if you like. So this moment, this second moment will cause buckling at this loading. But we do not want buckling to occur in that compressive member. So here I've chosen dimensions 27 by 27 millimeter. That gives you a second moment of 44,000. This is millimeter to the fourth, which is larger than this. So buckling will not occur if I use this square section. The area of the section is 729 millimeter squared. Okay, now I want buckling to occur at 500 newtons for the diagonals, and assuming a rectangular section, well, using the Euler formula, you can obtain a second moment of area of 7719. This is millimeter to the fourth. If you assume a rectangular section, I'm trying to get approximately the same area in all three members, equal areas. And if you assume a cross-sectional area roughly the same as A2, you can use these dimensions. The depth of the section is 11.27 millimeter. The width 64.7 millimeter. You get this area, which is approximately the same as this. And it will have this second moment also. So buckling will occur. Right? So we are assuming it has this cross-sectional, the second moment. So if you use these dimensions, it will have the second moment and this cross-sectional area. So buckling will occur also. I'm using A1 equal to A2 also, because I want equal areas of cross-section in all of them. So I'm using a cross-sectional area A1 equal to 729 also. So I'm assuming these cross-sectional areas and these dimensions. So buckling will occur at 500 in the diagonals, but not in the vertical member BD. Now, using those cross-sectional areas, according to our analysis, if we had compatibility, if buckling did not occur, then the diagonals would exceed the 0.5 kilonewton in compression. But once buckling occurs, the diagonal forces will be limited to 0.5 kilonewton. So this would happen under the given loading with the cross-sections that I've just calculated. Now there are two possible extremes. One extreme is for the diagonal member AD to be at its maximum length. And the other extreme is for the diagonal CB or BC to be at its maximum length. So there would be, so in this situation, this joint A would be furthest to the left, and in this case, the joint A will be the furthest to the right. Now you can look at I've calculated the displacements here. You can compare the two. Okay, so in this case, the joint A is displaced 0.046 millimeter to the right. In this case, 0.085 millimeter to the right. So it's slightly more to the right. In this case, the joint B is displaced 0.05 millimeter to the right. In this case, 0.09 millimeter to the right. So you can see here that in this case, these two joints are shifted about 0.39 millimeters to the right. So it's only these horizontal displacements for joints A and C that differ in both diagrams. All of the other displacements are the same. Okay. So in this case, the member AD is at its maximum buckling length. That's when it's still straight, it's just about to buckle. The other diagonal will be shorter, and therefore it will be slightly curved. So buckling has occurred in that, and there's a slight curvature. In this case, the member BC is at its maximum buckled length. That's when it's still straight, but just about to buckle. And in that case, the diagonal here will be shorter than that maximum buckling length, and therefore it will be slightly curved. This diagonal member will be slightly curved. So these are two extreme cases where buckling has occurred in both the diagonal members. Now, this is not catastrophic because the differences here in the two displacements, although I've exaggerated this highly here, the difference is actually very, very small, 0.039 millimeters. And you can see here that although equilibrium will occur in either of these two extremes or anything in between, the difference is so small that it will be imperceptible. So again, this shows that you can calculate deflections or displacements even after buckling has occurred, and the buckling may not cause complete collapse of the structure. It may just limit the structure to movement between two extremes. Now, I have not explained how I got these deflections, and I did it by calculation. I did it by a spreadsheet calculation, not by software. Okay, so some of you automatically run to software to calculate these deflections or displacements, but I'm saying that it is not absolutely necessary. What I'm showing here is my spreadsheet, a page from my spreadsheet where I calculate the displacements of these joints. So suppose you know the displacements, the vertical and horizontal displacements at joint C and D. C is fixed, so the displacement there is 0 and 0 in both directions. D is on rollers, so 0 vertical, but this is the length of the extension of the member CD. So this will, so 0.009 millimeters is the horizontal displacement of D. Okay, what I'm doing here is on my spreadsheet is given the displacements at C and D and knowing the elongations of the members AC and AD, I can calculate the displacements of this joint A. This is what my spreadsheet does for me. And yeah, these dimensions are just the vertical gap between C and A, and the 4,000 here, the horizontal gap between A and D, the vertical between A and D, the horizontal between C and D. And yeah, these are the computations I did with my spreadsheet. Okay, once you know the displacement at C and D and the extensions and the elongations of the members AC and AD, it calculates these displacements at C and D. So I'm just illustrating here that a spreadsheet is adequate to calculate displacements. You do not have to use vertical work methods. You do not necessarily have to use spreadsheets. You don't necessarily have to use software. Software is useful when you have large structures with lots of joints and lots of members. But for small structures, as in this example, it's not absolutely necessary. You can do these computations with spreadsheets. In another video, I will explain the mathematics behind the calculations, how I compute these things, and give you the formulae. But just look at these spreadsheets and be aware that it can be done without using software. Once again, thanks for following this video and the channel. Make comments if you want me to expand on anything or clarify anything. I will make new videos on those topics, so kindly let me know, make comments in the comment section. Please like and share. My name is Charles DeMatos from the University of the West Indies, St. Augustine, Trinidad.